Hello again. In this lecture, we look at functions. Functions are a tool in mathematics used to describe relationships between variables. And this is a very important part of mathematics. Everything's based around these. You will have seen some of these before. I will extend the ideas that you have seen before. First of all, thought of the day, let him who would move the world first move himself. You may change the world. To move the world, do anything at all requires effort. Move yourself. So first of all, introduction. We have simple cases that you would have seen before, like y equals 2x plus 1. Now this defines a relationship between the variables x and y. And for any variable, any value of x that I give, we can calculate the value of y. So for example, if I put x equals 2, I can work out 2 times 2 is 4 plus 1 is 5. And similarly, if I give a value of y, you can find the value of x. So I put y equals 3 here, you can solve the equation 2x plus 1 equals 3 and get x equals 1. In this case, what we find is that each value of x gives only one value of y. If I look at this equation, x squared plus y squared equals 1, when x equals 0, I get y squared equals plus or minus 1. So here, two values of y are possible for some values of x. So what we do is we restrict this a little bit so we can make some more sense out of this. We say y is a function of x if each value of x gives only one value of y. So in the previous examples, the y equals 2x plus 1 is the function, where the x squared plus y squared equals 1 is not a function. And we write this in this way. The f, or whatever symbol we use here, we can use f, g's, whatever else we need. But the x here indicates that this is a function of x. In other words, this is a relationship between x and something I'm going to give you. In other words, I'm describing something. Fx here describes a rule of some kind using x, and I can get values of the function in terms of x if I put values of x in there. The other two concepts here are that not everything is defined all the time properly. So the domain D of f is the set of the values of x for which I can compute x, I can calculate x. And the range R is the set of values the function can take. So in the case of y equals 2x plus 1, any value of x I can calculate 2x plus 1 for. And so this means the entire real line is the domain for this. And again, any value of y I can obtain given an appropriate value of x, or given a value of y I can find the value of x that gives me the value of y. Again, so y here is the entire real line. Sometimes, as you'll see, finding the domains of ranges can be quite tricky. Here are some examples. Fx of x squared. The domain is every real number, but the range here with x squared isn't all the real numbers. In fact, with x squared there, what I'm going to get over here is y bigger than or equal to 0. So the domain is all the real numbers, but the range isn't all the real numbers, it's only the non-negative numbers. Look at square root of x. Here the domain, the x's must be bigger than or equal to 0 because we don't take square roots of negative numbers. And the range similarly is all positive numbers, all bigger than or equal to 0, no negative numbers here. And that's because I'm taking the positive square root. Y equals 2x here. Again, the domain is in the entire real line. Any real number I can work out 2 to the x for. But the range is only the positives, but y bigger than 0. Because 2 to the x can't be 0, it can't be negative either. A quadratic of this kind over here. You can see I can factorize this here. Again, I can compute this for any real number. But look at how this works out here. If I look at this quadratic here, and if I plot it, what we'll find is it intersects at -1 and 3 for the real for the x-axis. So it looks like this here, 3 and -1. And I know the vertex here is the middle, which is 3 minus 1. The vertex is it's 2. And if I put 2 in the function, I get 4 minus 3. So in fact, this should be, I think I made a mistake with the -4. Let me check that again. The intercepts are 3 and 1, yes. And the midpoint of that, 3 -1, sorry. And the midpoint of this 3 minus 1 is 2. It's 1 actually, sorry. The midpoint here, 3 minus 1 is 2.5 of that. So this is 1 actually. My mistake. If I put 1 in there, what I find is that's going to be 1 minus 2 minus 3. So that's negative 4. That means y can't be, this is the minimum point here, negative 4. So y must be bigger than or equal to negative 4. So that's the range in this case. Notation we use here is when I have something like this where a and b in the endpoints are not included, then if I draw that on a number line, then I have circles with holes, unfilled circles at the ends. And I write them in in brackets of this kind, a, b, the usual brackets. If I include the endpoints, that means it's less than equal to, I can include the endpoints with less than equal to there in both sides, both c and d are in the interval. Then I have closed circles on both sides, and I use square brackets of this kind. So something like, for example, 1 to 4 means I have 1 to 4, and neither 1 nor 4 are included in this. So this essentially says 1 is less than x is less than 4. Whereas something like this, 1, 4 with a square bracket and a curly bracket, means 1 is less than x, but I do include 4 over here, which means if I sketch it, I get a 1 here, and I get a 4 here. That's an empty circle on the one side, and a full circle on the other side on 4, and that's my set of values there. That's the set 1, 4. So the domain are the x values, and the range are the y values. For this function, the domain is that bit sketched over there. The range is all the values of y that we can take from the function. Example over here, for the function fx equals x minus 1 square root of, find the domain. The domain here is going to be all the values I can define the function for. So I require here x minus 1 to be bigger than or equal to 0, because we don't take square roots of negative numbers. And that gives me x must be bigger than or equal to 1. So the domain here are the set of values that are real, x real, such that x is bigger than or equal to 1. So we read this as x is a real number, x is in the reals. This means element of or belongs to. The dots over here, the colon is such that x is bigger than or equal to 1. And the range here is going to be, well, it's a square root here, and so it'll be everything bigger than or equal to 0. So the range is the set of values y in R, y, the set of real numbers, such that y is bigger than or equal to 0. F at 2 is easy. F at 2 is going to be the square root of 2 minus 1, and that's just 1. F at 5 is the square root of 5 minus 1, and that's the square root of 4, that's 2. F at 0 is going to be undefined, because that is essentially square root of negative 1, so that's undefined. In other words, I don't have the square root of negative 1. F at u, so all I do is whenever I see x, I write u now. So that becomes u minus 1 square root of. And similarly, f at v squared essentially means whenever I see x, I write v squared. So it's v squared minus 1 square root of. So x actually is called a dummy variable. All it tells me is what I put in this location here. If I have a 5 in the brackets, I put a 5 there. A u in the brackets, I put a u there. A v squared in the brackets, I put a v squared there. Now, functions. We know that some relationship that we have is the function if for each value of x, I get only one value of y. So which of the following are functions? Well, in this case, you can very quickly see that x equals 0 gives me y squared equals 1, which means I get y is equal to 2 values. So not a function. This one here we know is a function, because for every value of x, I only get one value of y out of it. And this also is a function, because for any value of x, I get only one value of y out of it. So you have to look at the relationship and see what's going on there. A bit of thinking, a bit of insight, a bit of experience, and a bit of algebra will help. For graphs, we have this vertical line rule. So essentially the idea is that if I only get one value of x, if I get only one value of y from a value of x, that means if I draw a vertical line, that should cross the curve or the graph only once. Since the vertical line gives you a value of x essentially, and you must have only one value corresponding to that for y. So here are examples. You can see that if I've got two values of y for a value of x, then the graph will be intersected twice by any vertical line. So the vertical line must intersect no more than once. In fact, if it's not, if I look at something like square root of x, doesn't intersect, that vertical line doesn't intersect anywhere, but that's fine. But it can't intersect more than once. And you can see that's why the way it works is that if I have only one value of y for a value of x, the vertical line here represents a value of x somewhere. And I have only one value of y from there. So the first is the function, the second is the function. Some examples over here, a parabola here, that's a function. Vertical line test tells me this is not a function. Vertical line test will cross twice. Y equals root of x is a function, and this cardioid isn't a function either. Simple functions, the straight line functions, essentially linear functions, the domain of those, the things that look like y equals x plus c, the domain is all the real numbers, and the range is also all the real numbers. And so you know how this works over here. Y equals mx plus c here. So m is the slope of this thing. That means if I put an x equals 0 here, I get y equals c, that's the intercept there. And if I put y equals 0, I get x is going to be negative c on m. And the way it works is, if I take a difference here, if I go up 1 in x, and then that goes up by m. That's what the slope m here means. If I increase x by 1, y goes up by m, as you can see. And so some examples over here. Let's take a look at y equals x minus 1. Sorry, x plus 1 here. Y equals x plus 1. You can see the slope here is 1. When x is 0, y is equal to 1. So that's the y-intercept. So the c is the y-intercept. And the slope is 1. If I make it y equals x minus 1, you can see it is exactly the same slope, but now the intercept is negative 1, so it's going to go through here. And when x is 0, y is negative 1. When y is 0, x is equal to 1. If I take a look at y equals negative x plus 1, the intercept still is 1. It's a negative slope. Negative slopes go this way. As you can see, it goes the opposite to the positive slopes. Positive slopes, as x increases, y increases. Negative slopes, as x increases, y decreases. Here, as x increases, y also increases. So that's easy to pick up from there. And so we'll look at how to find the equations of these straight lines afterwards. Essentially, you can find very quickly the slope. So if I give you, say, 2 points like this, 0, 1, let's say, and 1, 1, then the slope here is the y difference. So the y difference and that difference, which is just 1 minus 1. Let me make this 2, sorry, that makes it a bit more interesting. The slope here is the difference between the y coordinates, the 2 minus 1, and in the same direction I subtract the x coordinates, the 1 minus 0. So that gives me a slope of 1. And so the equation of the line is going to be y equals, it's mx plus c. So the m here is 1, which is x plus c. Now I put a value in here. The value I can put in is when x is 0, y is equal to 1. That gives me equation y is equal to 0 plus c. So I get c is equal to 1 as well. And my equation here works out to be x plus 1. So again, I find the slope by looking at the y difference over the x difference, subtracting the same direction. And then the equation is y equals mx plus c. So the slope I found here, m I put in there, put a point in here, solve for the constant, you can get the equation. Here is y equals 2x plus 4 here. And so here, this is a function. And the domain here is all real numbers, and the range is all real numbers as well. So 2x plus c here, the slope is equal to 2, and the constant is 4. So now it will intersect with y equals 4. So it looks like that. That's 4. When x is 0, y is equal to 4. And when y is 0, x is equal to negative 2. There's my graph for that function. You can see a positive slope. Negative 2x plus 4. Now I know the intercept is still 4, but the slope is negative. So that's my 4 for the y-intercept. When x is 0, y is 4. When y is 0, now I get x is going to be 2. And you can see the slope here. The difference here is 2, and the difference here is 4. So if I look at the points here is 0, 4, and 2, 0. You can see the slope here, 4 minus 0 is the y difference, and 0 minus 2 is the x difference, and that comes to negative 2. The domain and range here are all the real numbers in both cases. Now here, I don't want you to get stuck on notation here. If you're able to simply write down the variables or real numbers, that's good enough for me. But it's nice if you can try and use the notation and get used to it. Quadratics here, we've seen them before, but we'll have a look at them again now here. So y equals x squared is a quadratic. The domain here, and we know, is all real numbers, but the range is going to be just y bigger than or equal to 0. So you've seen this before here. This is just the basic parabola, and again we've seen this in detail in the quadratic section when we were dealing with quadratic equations. We'll have another look over here. So this essentially is y equals x squared, something like that. And we can move this around, translate this, and so on, and scale it. So let's have a look at some of these. Y equals 2x squared simply scales it. So before the parabola, y equals x squared, if I draw that, you can see how these things change. This is y equals x squared. So the value here, 1, 1. But y equals 2x squared is going to be steeper. So the value here is going to be 2. So it's scaled, that's all. X squared plus 1, what happens here is I have the x squared and I'm shifting this in the y direction by 1. Once I've got x squared, then my basic parabola y equals x squared. When I add 1 to it, it just goes up to that point there and starts there as 1. Nothing else changes. The graph is exactly the same, but it's translated in the y direction by 1. So that's the translation in the y direction by 1. This is the first one is a scale. Of course, if I make it x squared and x squared minus 1, it's translation in the opposite direction, as you can see in this case. So there's my x squared. But with the minus 1, it now starts over here. So that's how these things work. Now, here's a more difficult one. X minus 1 squared. Well, not really so difficult. What's happening here is, the important thing to note is, when x is equal to 1 here, I get 0. So what's happened is, The origin used to be here. Think of what I have to do to this to get it back to 0. I will add 1. So it starts over here. So again, from here, if I subtract 1, I get back towards 0, right? So this starts, this is x minus 1 bit here. That means the vertex shifts to 1 over here. I subtract 1, I get back this way. That's what the subtract minus 1 over here gives me. So this is a different graph altogether. You can see very easily this goes through 1 here as well. And so this is translation in positive x direction of 1. Have a look at this one here. I can't factorize this, but I can write this as, so this is going to be x minus 1 squared. And so if I look at this, that part tells me it's an x minus 1 squared. But if I look at this, I get a plus 1 from here. We subtract here. So you can expand this out, you'll find it's the same thing. The way this works is this is called completing the square. And we haven't paid much attention to this. But the idea is I write this as a square plus something else that I need to maintain equality. And so I take a look at the coefficient of the x term here and take half of it. And that's what I put in here. So it's x minus 1 squared. But when I expand this, I get the x squared and I get the minus 2x. But I get the plus 1 as well, which I must subtract off, and that's why this is a minus 9. So I can draw the graph of this using the ideas I have seen so far. First of all, there is my x squared. Then it's the translation of, it's a minus 1, so it's a translation in the x direction of plus 1. There is the x squared, x minus 1 squared. And now it's a minus 9. So it's going to go down here to negative 9. So the vertex is this point here. So all the work I did so far here was to find the vertex, this point here. That's at 1 and 9. And once I have that, I've got the entire graph down here. I can find these x-intercepts and the y-intercepts easy. If x is 0, y is equal to negative 8. But the x-intercepts here I'll find by, well, let's have a look. This is actually x minus 4 times x plus 2. I can factorize this, I was wrong. So that's okay, x squared, I get a minus 2x, and so it's easy to see this will be a minus 2, and this here will be a 4. And as you can see, the midpoint of this is 1. So that's how these graphs are developed actually. By completing the square, this is a very strong idea. I can find the vertex straight away. Sketching quadratics, just in general here, we're going to find the intercept. So put y equals 0, that gives me the x-intercept. Put x equals 0 and solve, you get the y-intercept. To obtain the vertex, the coordinate of the vertex, the x-coordinate is always negative b on 2a. We saw this before. So here, the b is negative 2. And so vertex, the x-coordinate here is going to be negative b on 2a, and that comes to 1. As you can see, once I have the x-coordinate, I can put that back in the equation and work out the y-coordinate. So I find that, then I obtain the y-coordinate here. If the graph is 2 x-intercepts, then the midpoint is the x-coordinate, but sometimes the intercepts aren't easy to find if you can't factorize. If the graph has only one intercept, one x-intercept, then this is the vertex, as we saw in the square term. So this one here, which is essentially x minus 1 squared, only has a single vertex there, and so that is its vertex, and that is where the x-intercept is as well. So enough of that. We'll see more of this afterwards. Bye bye.